Hi, my name is Lucas Weintraub, and today we're going to be looking at transformations of sinusoidal functions. This video is going to have two parts. So I'm going to show you how to get a graph when you're given the transformations of a function, specifically in this form. And I'm also going to show you how to get a function and its transformations given the graph. So we're going to go forwards and backwards. Just as a quick refresh, sinusoidal functions can be modeled by one of these two things, and it's a times sine of b times x plus c all added by d. A is the vertical stretch, b is the horizontal stretch, c is the horizontal shift, and d is the vertical shift. You can use sine or cosine. It'll be the same, it's just the horizontal shift will be different by pi over 2 because sine and cosine are the same function but with a horizontal shift. Now I'm going to show you what each of these shifts look like. So A, although is a vertical stretch, it's also known as the amplitude for sinusoidal functions. It's also the distance from the midline of the wave to the maximum. I'm going to pull up Desmos here to give an example. So the purple wave is the regular cosine function, and the green wave is a regular sine function. And using this slider, I'm going to show how you can see that these waves stretch up and down. Their center doesn't move because their center has a value of 0. But the rest, it kind of just stretches. And when I make a negative, it flips over the x-axis. And so, like, if I were to make a equal to 3, this distance right here is 3. 1, 2, 3. So that's the distance from the middle to the maximum. And so if you have an amplitude of 3, this space right here is going to be 3 as well. Now moving on to horizontal stretch. So the horizontal stretch is how much you stretch it out left to right. So kind of the same for vertical stretch, but the math for it is a little different. So the way I would describe it is the ratio of the normal period of the function to the new period. And the period is equal to 2 pi over the absolute value of b. And so by rearranging that, you would get that the absolute value of b is 2 pi over the period. 2 pi is the regular period, and so basically it's just the ratio of the regular period to the new one. And so I'm going to pull up Desmos again. Let's make the amplitude normal. And if we were to change b, you can see that the function stretches out as we get less than 1, or as we get within -1 and 1. And as we get greater than 1 or greater than -1, it stretches. And so I like to think of horizontal stretches as as b gets bigger, it's wiggling faster. And so that means each of these little, that means the period gets smaller, because if you're going faster, then this gets squished. And if b gets smaller, then the period gets bigger because you're going slower. And b is on the inside, so you're changing the inside, the x. And so when b is small, this is kind of slow, and so that means the period is bigger. And that's why people say that x's are wrong, because with the amplitude, as a gets bigger, the stretch is bigger, but for b, as b gets bigger, the horizontal stretch gets smaller. Now let's move on to horizontal shift. And this is the letter C. So this is just the change left to right of the function, just like the vertical shift. And x's are wrong, and so if you have like x plus 4, that means a shift 4 units to the left. And if you were to have x minus 4, that would be 4 units to the right. I'm going to show that on Desmos again. So I'm going to make this 1. And C, if we make C positive, it moves to the left. And if we make C negative, it moves to the right. So if we had like C is equal to -2, that means the middle of the sine function, this is kind of like the middle, is going to be at 2 instead of 0. So we moved it 2 to the right. And the top of the cosine function, which is kind of like the middle for the cosine, is also going to be at 2 instead of 0. Now, lastly, the final letter is the vertical shift. And so this is D, and it's the midline of the wave. And so it's really simple to understand. Here, the middle of both of these graphs is 0, kind of like the average between the top and the bottom. And if we were to shift it up, like let's say D is equal to 2. The middle of the height, which is like right here, is at 2 instead of 0. So let's try to graph a function with all this knowledge. Like f of x is equal to 2 times sine of 2 times x plus 1 minus 1. So what would this look like? The easiest thing to do is to graph a point and see where it moves. And so this is sine, and sine takes this shape, so kind of like that, which means it starts at the origin. And let's see how the origin moves. This doesn't, the stretches like 2 and 2 doesn't change anything because this is at 0, 0. Multiplying by 0 doesn't do anything. But adding 1 and subtracting 1 does move it. So let's see, -1 for a vertical shift, that will move it 1 down. So now it's here. And +1 means a horizontal shift to the left. So now we've moved it here at this point. So all in all, now the middle of our sine function is here. Now let's try to find the vertical shift, or the vertical stretch, sorry. So the vertical stretch is 2, which means instead of the maximum being 1 unit away, it's going to be 2, because the distance from the midline to the maximum is going to be the amplitude, which is 2. So this is going to be as far as it goes on the top, and this is as far as it goes on the bottom. Now, this 2 means that the period is going to be half as big, because x's are wrong, and so it's just going to be the opposite. And so if 2 is on the inside, it's going to be half. And if instead we had 2 sine 1/2 of x plus 1, the period would be twice as big. So just the opposite. Here, since our case is 2, the regular period is 2 pi for sine, and that means now our period is going to be pi. So the next time the sine function hits this point is going to be pi away, which is right here. And it's going to repeat again right here and here, here. And this, the graph of positive sine goes like that from the middle. So we're going to have the maximum here, and then the minimum here, and the maximum here, minimum there, and it just goes like that, and it continues on and on and on. By the way, the maximum is in between the two middle, and the middle is in between the max and the min, And so basically everything is just in between each other. These are all of these are the same distance. So just like split it in half and just know if it's positive or negative, and you'll know whether to go like this or like this. So now that we've gone forwards and found a graph given the function, we need to find the function given the graph. So we're going to go backwards. And to do that, we need to just find the four variables, a, b, c, and d. And we're going to use a four-step process, one step for each letter. First, we're going to find d. And I actually have a function prepared. So imagine you have a function like this, and you want to figure out, or you have a graph like this and you want to figure out the function. The first thing that we're going to do is find the midline. And so the midline is just going to be the middle, and it looks like right about here, and it's -2. But if you didn't want to guess and you wanted to use math, just find the average of the top and the bottom. Because it's the midline, it's going to be in the middle of the top and the bottom. The top of this is 0, 1, so the top of this is 1, and the bottom of this is -5. And so the answer to that would just be the sum of those, and then divided by 2, which is going to be -2. So we have that our d is -2. Now let's find our a. So a is the amplitude, also known as the distance between the middle and the top. And this happens to be 3 because we found that the middle was -2 and the top is 1, and the space between that is going to be 3. So that means our amplitude is 3. Now let's find b. So b is how often the graph repeats. And the graph repeats whenever you go from one maximum to the next, or from one middle to the next. It doesn't really matter which one you choose, just as long as you find the next time it repeats. And so this, this starts at 0, and the next time it's at a maximum is at 4. So that means we have a period of 4. So our period is 4. And the formula for period is equal to 2 pi over b, which means that rearranging, we get that b is equal to 2 pi over 4, which means b is equal to pi over 2. Now, our last step is to find c, and I left this for last because it's the trickiest part. The reason why is because this graph can be described using either sine or cosine. So there's two different cases. So let's try to do cosine first. So if this is cosine, it's going to have no shift because the maximum is centered at the middle. And the regular cosine function has the maximum centered at the middle. And so we didn't move it left or right at all. So if the answer, since c is equal to 0 for this case, plus a period, the answer is going to be 3 times cosine of pi over 2 x minus 2. Now let's do sine. So if this is sine, sine starts here at the middle of this little upward slope. So we just need to see how far this has been moved. So this point is at -1, and so we moved the graph 1 unit to the left. And the transformation of 1 unit to the left is the same as x plus 1. So that means that our function for this is going, for sine, would be sine 3 times sine of pi over 2, and then x plus 1. And then all minus 1. Or minus 2, because that's the actual midline. And let's reveal what the actual function was, and it was exactly that. And so there's always more than one answer to things. If I were to write another function like this and do cosine, like so, let's see, pi over 2, and then x, and then all minus 2. It's the exact same function. So there's always more than one answer, and that's why I recommend that if you ever have a multiple choice question, just do both cases and see what works. And sometimes if neither of these answers are available, you might just be off by a period. So you might just have to add like pi over 2 or just whatever your period is, and you'll probably find the answer. So I hope that now transformations of sinusoidal functions makes a little more sense.